All right, guys, 13.2, we're talking about permutations and combinations today. Yesterday, or last time we met, we talked about counting and the possibilities when we're counting. And so today, what we're doing is, this is a form of counting, but now we're bringing in the fact that we could repeat digits or repeat letters or things like that. So permutations, combinations. A permutation is an ordered arrangement of R objects chosen from N objects. Okay, so this language just gets super weird and kind of confusing when you're first learning it, but just know this. N is the number of total distinct objects that we're looking at. So if we were talking about an alphabet, N would be equal to 26. R is the number of selections that we want to make. So for instance, the classic example, and we're going to do one like this in a bit, is give me a 10-letter code from the alphabet. How many possibilities do we have for a 10-letter code? So in that case, the R value is the 10. It's the number of selections that we're talking about. Okay, so if we were talking about a 10 letter code, then R would be equal to 10. Okay, so let's look at this. It says the N objects are different and repetition is allowed in the selection of R of them. What this is saying is we have distinct N objects like alphabet, digits, something like that, where we have a distinct difference between them. And it says repetition is allowed in the selection of R of them, right? So what this is saying is I can use, like if I was doing the alphabet, I could use A, if I was finding a 10-digit code, the first code, or not digit, but a 10-character code, the first code that I could get, it would be A, 10 A's, right? So A can be repeated a number of times. So we're going to look at those possibilities with repetition, and that's permutations. The second one is we could have N objects that are distinct, so like letters in the alphabet, and in this case, repetition is not allowed. Okay, so if it's not allowed, it's much like what we were doing with counting yesterday. And then for number 3, it says the N objects are not distinct and all of them are used in the arrangement. Okay, so what happens when everything is used in the arrangement? And what we'll see with that is we include, like, N and R essentially become the same thing, where we have, if I used every character in the alphabet, N would equal 26, and then my selections, if I used every single one, R would also equal 26. Okay, so we'll do a problem that's related to that. Now, theorem 1 states this: the number of ordered arrangements of R objects chosen from N objects in which the N objects are distinct and repetition is allowed is N to the R. So I'm just remembering that Adam last time was asking about, well, what happens if you have a dice? Does the base change to 6 when you have 6 possibilities? Well, it does. It would, not in the counting principle, because in the counting principle we were just looking for subsets of the dice, right? So in the counting principle, the answer to this question would be, okay, if we're just looking at subsets of a die, it would be 2 to the 6th power, because there's 6 faces to a die. To a dice, I should say. Okay, so that's the number of possibilities we have within those are the subsets that we would have with a dice. But, and I could work on another example with that with you guys next time, just to show you how that works. But this one today is talking about if you have N to the R, which is what happens with a permutation where repetition is allowed, what we're saying is that N is the number of possibilities, so on a dice that would be 6, and R is the number of selections. So say we had 3 die. If we rolled 3 die, what's the possibility, or what are the possible combinations that would happen? That would be 6 to the 3rd power. Okay, so 6 to the 3rd power would give me the total possibilities for rolling 3 die. So that's the difference between looking at like the possible, combinations, like when you're counting, would always be a 2 base 2 to however many, sides of a dice there are or whatever. But the permutations looks at the possibilities raised to the power of the number of selections. Okay, so example 1 says the International Airline Transportation Association assigns 3-letter codes to represent airport locations. For example, the airport code for Fort Lauderdale is FLL. So it says, notice the repetition is allowed. Yeah, we have an L and an L, so we can repeat things twice for forming this code. How many airport codes are there possible? Okay, so we're talking about something where we have repetition, right? We could have an airport code that's AAA, for instance. Repetition is allowed. Okay, we have 3 selections that we're trying to make, and there are 26 possibilities. So we could say, okay, for the first letter, we have 26 possibilities. For the second one, since repetition is allowed, we have 26 again. And then for the third one, we have 26 again. Okay, so we, by multiplication principle, 26 times 26 times 26. Or this is the same thing as taking 26 to the third power, right? So that's where this kind of idea comes from. But imagine, you guys, just for a second, if repetition is not allowed. So if you use a letter, you can't use it again, right? So then so this is kind of a side note, separate problem here, but if repetition was not allowed, then for the first selection of our code, we would have 26 possibilities. But then for the second piece, we could not have 26 because one letter is taken away. So if repetition is not allowed, then for the second one, we would have 25. And then for the third one, we would have 24. Okay, so that right here, that idea is where we come up with the next theorem. Okay, so for the next theorem, it says if we have the number of arrangements of in objects in which the in objects are distinct, like letters of the alphabet, and 2, once an object is used, it cannot be repeated, like we just talked about, and order is important, we have this formula where we have in factorial. Okay, so if we did this using this formula, we'd have 26 factorial all over n minus r. Okay, and in this case, r was 3, so we'd have 26 minus 3, or 26 factorial over 23 factorial. Well, just a reminder of what a factorial is. It's like saying 26 times 25 times 24 times 23, dot, 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 all the way down to 1, right? So if we had that over to 23 factorial, and we think about what that is, notice that from like 23 down, everything would cancel, and we'd be left with this guy, right? So that's where that formula comes from. Okay, and just remember, n is always the total number of distinct objects, where r is the number of selections that we're talking about, trying to make. Okay, it's like the number of digits or characters in a code or something like that. That would be your r value. Okay, so for example 2, it says suppose that a 4-letter code is to be formed. Okay, so that's like your selections, right? So that's the r value. R is equal to 4. Using any of the 26 uppercase letters of the alphabet. Okay, so those are your possibilities. That's n. Okay, but no letters to be used more than once. So no repetition allowed. Okay, how many different 4-letter codes are there? So we would use this guy where we have no repetition allowed for permutation. We have 26 factorial over, this would end up being 22 factorial, I believe. The 22's cancel out, and you're left with 26 times 25 times 24 times 23. And let me see what that is. That comes out to 358,800 possibilities. Kind of cool. All right, so example 3. It says, in how many ways can 6 people be lined up? So example 3 deals with like the third type of permutation where we use everything in the arrangement. Okay, so there are, the objects are not distinct and all of them are used in the arrangement. Okay, so in this case though, we do have 6 distinct people. All right, so 6 distinct people, but we want to see all of them used for, right? So we have 6 selections, 6 different distinct people. So you can think about that as we have 6 selections that we're making, so R is equal to 6, and then N is 6. We have 6 distinct people. So how I would figure this out is I would take 6 factorial over 6 minus 0, sorry, 6 minus 6 factorial, which is equal to 0 factorial. Okay, which is just going to be that 0 doesn't cancel anything out, so we're just going to have, let's see if I can get my pen to work again here. What's going on? Pens, I want red, sorry guys. So this would be 6 times 5 times 4 times 3 times 2 times 1. Let's see if I can do this one in my head here. This would be 30 times 4, which is equal to 120, times 6 is 720, I believe. So 720 possibilities of 6 people lining up in a room. And yes, so if I said 5 people, you know, that would be very easy to figure out. That would be what? 5 people is quite a bit less. It's interesting how that changes. But we wouldn't include the 6, so it would be 20 times 6, which is 120, right? So only 120 possibilities if there's 5 people in the room. So it grows pretty quickly there. For example 4, and man, if we were in class, I would try to have you guys come up with all 120 before the bell rang. It should be fun. But hey, example 4, and we're only going to go up to example 5 for today, you guys. We'll do combinations next time, so just want you to start your homework and do the permutation stuff. But example 4 says they just want you to evaluate these things, like use a calculator and come up with it. So this is just saying find out what 6 taken at 2 is, you know, so 6 factorial. Remember that this would be, the bottom digit here is not 2, but it's 6 minus 2, okay? Because this is like N and R here. All right, so they want you to do that. So this is 6 factorial over 4 factorial. Notice that the 4, 3, 2, 1 would cancel, and you'd just be left with 6 times 5, which is 30. And then for the other one, this one here, we had 5 factorial over 5 minus 1 factorial, which is 5 factorial over 4 factorial. The 4's 4, 3, 2, 1 cancels, and you're left with 5. Okay, for C, this one looks a little daunting. You could do this one 2 ways. I'm going to teach you how to do it on a TI using the probability function, like there's a statistics function in your TIs, but I will also just show you how to, I mean, this one's not too bad. So this one would be 62 factorial over 62 minus 4 factorial, or 62, I don't know why I wrote 62 factorial over, so 62, so this would be what, 58 factorial? So the 58 through 0 or through 1 cancel, and so you're left with 62 times 61 times 60 times 59. So you could do that in your calculators. Okay, so we'll do that, and then I'm going to show you another way. So pull out your TI right now if you have it, so that you guys can get used to this. So we could do a 62 times 61 times 60 times 59, and we would get this, what is it, 1 million, is it 13,388,280, something like that? Okay, so we could get it that way, or let me show you another way. You could pull up your TI, you can hit the math function, the math feature, so I hit math. Okay, and then at the top here, I'm going to choose PRB. And then notice that the second option is NPR. All right, so the formatting is just a little different than what we're used to, but NPR, so we're going to put the N value in, and then they'll calculate the P, which is the permutation, taken at R, right? So I'm going to hit enter. So let's see if we get the same answer here. So for this one, we would have 62, right? 62 is our N value, and our R value was 4, I believe. And that will figure out the factorial for you without you having to put in the 62, 61, 60, 59. Kind of handy, could come in handy when something is not as easy as this and you'd have a whole ton of these to do, which I think maybe the next one is kind of like that. So let's just pull that back up. Example 5. all we know about Gabby and Ellie, hey, those names sound familiar, is that they have different birthdays. If all the possible ways this could occur were listed, okay, so if you think about that, that's like saying, okay, and assume that there are 365 days in a year. So we can't have a repeated birthday, but so let's just say we knew that Gabby's birthday was January 1, right? If we knew that, which we don't, all the possibilities would be for Ellie would be every single day other than January 1, right? So it'd be pretty simple to figure out. But since we don't know that, we have to list all the possible combinations of every single date, right? Every single date, and there's 365 days in a year. So you can imagine where doing this kind of a calculation on your calculators would not be a super fun thing to do, especially if you didn't know the rule. But the rules make this actually very simple. We know that we have 365 possibilities total, right? So 365 is our n. And then we know that we're only looking for R, for the selection here, the number of selections, R is simply 2. We're just looking for 2. And there's no repetition. Okay, so we're just going to use our factorial. It's pretty simple. This will be 365 factorial over 365 minus 2 factorial, which is 365 factorial over 363, which is really not bad, right? Because 363 and all the way down to 0 cancel, and I'm just left with 365 times 364. Easy to do that on your calculators. You get 132,860 possible combinations of different birthdays with no repetition of a birthday. Okay, so an interesting example would be like what would the possibilities be if there was a repetition? Like what if they could have the same birthday, right? So you can think about what you might do if they did have that. So which one of these would that be? That would be like example 1, where repetition is allowed. So for that, hopefully, you know, if you thought about that, or if you haven't, pause the video. But for Gabby, you'd have 365 possibilities, and then for Ellie, there would be 365 possibilities. You multiply the two together, and if there's a possibility that their birthdays are the same, it would just be whatever that comes out to. Not much different than the other, but definitely will add a little bit. Okay, I think that is all, you guys. I'm going to pick up with combinations next time. Sorry for the video lesson this time, but hopefully this helps get you started, and we'll see you guys next time.